Good afternoon, Assistant Professor Dr. Niti Yonit and all my friends. Today our group which consists of กิรติพรบุญขำ ชนาธรปะทะดวง บุษกรชูแก้ว ปวิตากระจกเนียม ปิญญพัฒน์อดทน วลินทรธนกุลวัฒนา and สุนิสาบาปะเท extremely ready to present about enhance the photocatalytic activity of Deacon Derpsin Coxide thin films, morphological optical the next place photoelectron spectroscopy analysis written by Abdel Wahab. What we want to present today is introduction, objectives, experimental results and discussion and conclusions. For introduction, photocatalysis. The word photocatalysis is a composite word which is composed of two parts, photo and catalysis. Catalysis is the process where substance participate in modifying the rate of the chemical transformation of the reactant without being altered and consumed in the end. This substance is catalyzed, which increases the rate of the reaction by reducing the activation energy. Photocatalysis. Photocatalysis is a reaction where using light to activation a substance which modifies the rate of the chemical reaction without being involved itself. And the photocatalyst is a reactant which can modify the rate of the chemical reaction using light irradiation. Semiconductor photocatalysis. Semiconductor photocatalysis apply to a variety of problems of environmental interest in addition to water and air purification. It's useful for Semiconductor photocatalysis apply to a variety of problems of the environmental interest in addition to water and air purification. It's useful for destruction of bacteria and viruses, for the inactivation of cancer cells, for odor controls, and for cleanup of oil spill. Zinc oxide is one of the promising materials due to its non-toxic, high photocatalytic efficiency and low cost. But pure zinc oxide has a drawback of fast recombination, and which ultimately affects its photocatalytic efficiency. This problem can resolve by modifying the zinc oxide thin film and doping the transition metals. In this case, they showed nickel metal doping because low cost our other metal, and this film prepared by direct current radio frequency magneton scattering. And objectives of the research. First one is to study the nickel zinc oxide thin film with highly enhanced photocatalytic activity. Second one is to study the degradation of metal green waterfall depending on the nickel concentration. And the last one is to study the change in the chemical state of zinc oxide thin films with the nickel doping.
And next, experimental. The thin film preparation uses direct current radio frequency magneton scattering technique to deposit thin film on the glass substrate. Substrate have been cleaned using ethyl alcohol and deionized water, then dried using nitrogen gas. And this table shows parameter control in their experiment. It means in experiment were prepared with control base pressure, operating pressure, deposition time, substrate temperature, direct current power for nickel target, radio frequency power for zinc oxide target, and argon fluid in the system. Photocatalysis experiment. In photocatalytic, they study this property of thin film. Their They use UV visible technique with wavelength in the length of visible light. They observe degradation of methyl green and obtain the degradation percentage from this equation. Where C sub 0 is initial concentration of methyl green and C sub T is concentration of methyl green at time during the catalytic reaction.
An important aspect of material science is the characterization of materials that we are use or study in order to learn more about them. So after preparing this film, they has to characterize them too. This film was prepared by the recurrent radio frequency magnetron sputtering technique. There are several techniques for characterization, but in this research we use 4 techniques for characterize. The first one is X-ray diffractometer or XRD. X-ray diffraction techniques are used to investigating the crystalline nature and the phase of thin films. It used Bragg's law for explanation in this work, and it can be calculated by the following equation. That is used to analyze the structure within thin films, such as grain size was determined by the following equation. The texture coefficient of each plane was calculated through the following equation. The dislocation density of thin film was calculated by the following relation, and the lattice strain was calculated by the following equation. The second one is atomic force microscope, or AFM. The surface roughness is the one of the most important of thin films. So, an atomic force microscope used to analyze the surface topography of the films. The third one is UV visible spectrometry. The optical characterization is based on the analysis of incident, transmittant, and reflectance of films. So the UV visible technique used to analyze the optical property within thin films. The last one is X-ray photoelectron microscope, or XPS. X-ray photoelectron spectroscope is a surface-sensitive qualitative spectroscopic technique that is used to study the surface composition and the analysis of composition.
Resource and discussion. In the part of structure analysis, Figure 1 shows the X-ray diffraction spectrum of zinc oxide film with different nickel doping concentration. We observe that the peak from the X-ray diffraction correspond to 100,002 and 101 pairs of zinc oxide hexagonal Wurtzite structure. In order that diffraction peak at 002 increase when doped nickel and decrease when nickel concentration increase. At 7%, diffraction peak at 002 disappear due to the substitution of nickel to ion into tetragonal size of zinc oxide Wurtzite structure. In Figure 2, this shows X-ray photoelectron spectroscopic results for confirm that the defect increased when nickel concentration increased. In Table 2, shows structural parameters as grain size, dislocation density, lattice strain, and texture coefficients. It can be seen that the grain size in column T increase when nickel concentration increase due to the nickel contribute to expansion of zinc oxide. But in nickel 7%, the grain size will rapidly decrease due to due to nickel content over 7 weights percent is beyond the solid solubility limits of nickel in zinc oxides. Half of nickel ion does not enter the crystalline structure of zinc oxides and crystalline forming nickel oxide grains. Figure 2 shows atomic force microscopic topographies of zinc oxide with different nickel concentration. In table 3 is atomic force microscopics from previous figure shows mean grain size and mean roughness. It can be seen that the mean roughness increase when concentration increase.
Next, the optical properties. This figure shows the optical transmittance of pure and nickel-doped zinc oxide thin film that investigated by UV visible spectrometry technique. The x-axis represents wavelength and y-axis represents the percentage of transmittance. From this figure, the results show that pure zinc oxide thin film have about 80% transmittance, in visible regions. But when they are doped nickel into zinc oxide thin film, the optical transmittance of this film fall to decrease. When increase nickel concentration. This continuous decrease in transmittance is because the formation of lattice effect, which arises due to nickel ion incorporation into zinc oxide matrix. This ion may occupy interstitial site on zinc oxide lattice and increase the absorption of light, thereby decreasing the transmittance. From previous slide, I have mentioned about the absorption of light decreasing when increase nickel into zinc oxide matrix. The absorption is related to the band gap energy. That's what decreased when increased nickel concentration. From this slide, the figure shows the optical band gap energy of pure and nickel-doped zinc oxide thin film. And the optical band gap energy was determined by this equation. From this figure, we can see the optical band gap energy of that's what decreased from 3.2 electron volt to 1.4 electron volt at different nickel concentration. This is because the shift in band gap energy is related to the band gap energy is decreased and cause increase the absorption of light.
The next characterization technique is about surface analysis. The instrument is called X-ray photoelectron spectroscopy or XPS. It measures the energy from core electrons that emitted from material. So you will know every element that is in the sample. The data we get is the spectrum that plotted between intensity and lighting energy. And this is an overall scan. It allows us to see the entire spectrum of their thin films, which basically the element that is in the sample. The area below those peaks are related to its amount in the sample. They call it as atomic concentration. The result shows that pure zinc oxide thin films consist of only oxygen atoms and zinc atoms, and thin film that contain nickel doping consists of oxygen atoms, zinc atoms, and nickel atoms with correct ratios and no contaminants. Again, back to this overall scan.
We are going to take a closer look on these nickel peaks, oxygen peaks, and zinc peaks. This is high-resolution breakdowns of nickel 2p signal. Because pure zinc oxide thin films has no nickel element, so the data here starts with nickel concentration of 3.5, 5, and 7 weight%. And in the last picture, it compares our sample with different nickel concentration. And because there are three important peaks at the binding energy about 853, 856, and 861 electron volt. So let's start with the first peak at the lowest binding energy. It's the main peak of nickel 2p signal, and it also belongs to nickel metals. In the last picture, you can see obviously that the amount of nickel metal is increasing as nickel concentration increases. Move to the second peak. They stated that it might arise from nickel 3+ species, but some other researchers suggested that it could belong to nickel 2+ species as well. And this nickel 2+ species bonded to hydroxide ion in water. And on the last peak, it shows that this species of nickel has the highest binding energy. They call it as shake-up satellite peak. This line can happen when there's the two different electronic configurations in final state. So the presence of this peak is characteristic for nickel 2+ species. It was assumed to charge transfer transition between 2p orbital of oxygen atoms and 3d orbital of nickel atoms, or to make it sound easier, there are hybridization of these atoms.
Let's zoom in the oxygen peak. There are two interesting peaks with different binding energy. The lower one shows that there have amount of high oxygen peak, oxygen atom. This oxygen can bond with zinc atom in wood-side structure. Another peak is telling us that these oxygen atoms have higher binding energy. So these oxygen atoms are bonding with nickel atom on the surface of thin film. The amount of interstitial of oxygen atoms are higher when nickel dope concentration is increased. But with higher nickel concentration, the shake intensity of both peaks decrease because of decreasing oxygen and zinc bond. Here is the last zoom at zinc peak. Intensity are decreased with increasing nickel concentration. This may cause change of film morphology.
And that is a result of photocatalytic activity. This graph in figure 9 shows the degradation rate of methyl dye, which plot between the degradation in y-axis and times in x-axis. It can be seen that the degradation increases by increasing of nickel doping percentage. With higher nickel concentration, nickel will incorporate in the structure and oxygen vacancies occur to balance overall structure. This results in increasing of surface roughness and the reactivity of surface. That is why there are more degradation when nickel concentration increases. This is Langmuir-Hinshelwood kinetic model. It can use to follow the composition of methyl green dye, where C sub 0 is initial concentration of methyl green dye, C sub T is concentration of methyl green dye at time, and K sub APP is apparent rate constant. From Langmuir model, apparent rate constant or K sub APP is the slope, which plot between log C sub T by C sub 0. Which plot between ln c sub 0 by c sub t in y-axis and a radiation time in x-axis. This slope appears as linear, which means it is pseudo first order. And the last one is conclusion. Pure zinc oxide and nickel-doped zinc oxide thin film have been synthesized by direct current radio frequency magneton sputtering technique effectively. It increased mean grain size from 27.9 nanometer to 34.76 nanometer, and surface roundness increased from 1.98 nanometer to 3.04 nanometer with nickel doping at different concentration. The reduction in band gap from 3.2 electron volt to 1.4 electron volt with nickel doping at different concentration. And X-ray photoelectron spectroscopy revealed the increase in surface effects with nickel doping at different concentration. Thank you for your attention.